Redaction. Polynomials as products of factors is what we're looking at. The word product is another name for times. Factor is something we've looked at. Our learning intention is to sketch polynomials in the form of y equals x take a to the power of m, etc., and know how multiplicity impacts the type of turning point. In fact, that shouldn't say turning point. That should say the type of x-intercept. So product of factors, we know that y equals x take 3 squared gives a turning point, and that x take 5 to the power of 3 gives a point of inflection. We also know that for y equals x take 3 is a factor, and the graph would cut the axes at the x-axis at 3. So we can call something like y equals x take 3, x plus 7 squared, a product of factors. Now what that means is there are two factors, x take 3 and x plus 7 squared, and there's a little times between those two things. So another way of writing this guy would be y is equal to x take 3 times x take 7, and because that's squared, times x take 7. So product, meaning times, of factors. This is a product of numbers, real numbers. This is a product of factors. This product of factors would have x-intercepts at 3 and 7. What the hell is multiplicity? Of course, that's going to be one of our definition words for today. So different factors have different multiplicity, and different multiplicity means different types of x-intercepts. X take 3 has a multiplicity of 1, x plus 7 to the power of 3 has a multiplicity of 3. 3, the power of 1, the power of 1, we just don't write the power of 1 there. So, as we said, different multiplicities have different types of x-intercepts. For example, this graph here, x take a to the power of 1, x take b to the power of 2, x take c to the power of 3, x take d to the power of 1 would cut the x-axis at x equals to a. So single zero from the factor of multiplicity 1. Touch the x-axis at x equals to b, and that would look like this. That touches the x-axis. That hasn't quite touched, but that's meant to. Saddle cut the x-axis at x equals to c. A saddle cut happens at 3, a touch happens at 2, and a regular old cut happens at multiplicity 1. And then regular old cut the x-axis multiplicity 1. And a graph can confirm that. So if we were able to graph that and put numbers in, we see that at point A we've got a regular old cut. At point B it just touches there. At point C there's a saddle cut, so sort of like a cut, but it's x to the power of 3. And at x to the power of 3 we have a point of inflection. That's it there. And then at D we've got another regular old cut. So what we can do is use this knowledge to more easily sketch polynomials, and we're going to take a look at an example now. So what we're going to do is sketch the graph of, whoops, that should have a y equals at the front there, x plus 2 squared to take x to the power of 3. Now sketching this doesn't look like too much trouble, except for this 2 take away x. This is meaning in my mind that it's been reflected somehow because we've got a negative x factor out here. But let's cross that bridge a little later. First up we're going to calculate x-intercepts, and we're going to think about the nature of those x-intercepts as well. So x-intercept is y equal to 0. So x-int y equals to 0. So 0 is equal to x plus 2 squared 2 take x cubed. We can apply the null factor law here, which is kind of handy. And then whenever I'm trying to solve something, solve a polynomial, I often look to the null factor law. I can use the null factor law here because we've got two factors times by each other. That means we've got x plus 2, and of course because it's equal to 0. X plus 2 squared is equal to 0, and 2 take x cubed is equal to 0. I'm going to pause the video, go ahead and solve this to save a bit of time. So as you can see, I've solved that there now. We've got negative 2, 0, because that factor is this guy up here. this guy is this guy, it's going to just touch the x-axis because that's a multiplicity of 2. This guy over here is this guy down here, and so he's going to saddle cut because multiplicity of 3. Saddle cut him there. So next, moving on, we want to go down and calculate the y-intercept. Y-intercept, that x equal to 0. Y-int, x equals to 0. And again, I'll pause the video, I'll go ahead and solve it. There, that is there, so that x equals to 0, and solved it, it turns out it's y equals 32, so a 0, 32 y-intercept. The last thing I want to do is just think about the order. Now the degree of the polynomial. The degree of the polynomial is how big the biggest x term is. So if x to the power of 4 plus 3x squared, the degree would be 4. So what we can do is this neat little trick where we just look at the highest possible factors. So we've got y is equal to 2 plus x plus 2 squared, and 2 take away x cubed. If we were to expand this set of brackets out, the highest term we'd get would be x squared. That'd be the highest term. Let's just have a look at that. In fact, I won't do that to save your time. But if you need to expand that, which is equal to x squared, x plus 2 squared, expand that out and see whether or not this is the highest degree of x you get. So you can put a bracket around him. Similarly, if I was to expand that, which is the power of 3, I would get x to the power of 3 as my highest term. So if I have x squared times by x cubed, I end up getting x to the power of 5. And that's even a negative sign there because that negative comes from this guy here. So that means the degree is 5. And so now we need to sketch this bad boy. We've got our points, we need a Cartesian plane. Let's grab him up. Where'd you go, Cartesian plane? There's our Cartesian plane. What I'm going to do is go a scale of 2 along the x-axis. Oops, sorry. Scale of 2 along the x-axis. 2, 4, 6, 8. And then -2, -4, -8. And then here I'll make that 10, 20, 30, 40. And negative down the bottom here as well. We've got our arrows, we've got our x and y axes labelled. We know that we've got a point at -2, 0 and 2, 0. So let's go ahead and put that guy in there. So -2, 0 is here, is a brighter colour, and 2, 0 is here. Oops, I did that round the wrong way, you get the idea. And our x-intercept, y-intercept is at 0, 32, which is, let's go there, just above 30. So now what we need to do is join these dots up in a way that's going to make sense, because -2 was going to be, what was that one? That was going to be a touch, I think. -2 was going to be a touch, and +2 was going to be a saddle cut. So which way can we do this? We've got a negative x term in there somewhere. If you're not too sure, like I'm not at the moment, let's just have a guess. We need to saddle cut here, so coming down, saddle cut and back through. Wait, that's not going to work because I'm not going to be able to bring that back around to go through these points, so let's get rid of that guy. So it must instead saddle cut the other way. We must come from up here, saddle cut through there. We've got a y-intercept here, we must have to turn back around and cut down. Oh, that's not a cut. That's meant to be a turning point and a touch. So if you could just ignore that bit there. Let's to try and fix it up a little bit. That makes it a little bit better, but that's meant to be a saddle cut. I would definitely lose marks for that. But as I say, this drawing pad is hard to draw graphs on. Let's take a look at some definitions. And the definition is multiplicity describes the number of times a factor appears. So x to the power of 3 has a multiplicity of 3 because it appears 3 times. X to take 3, x take 3, x take 3, 3 times. We can use a multiplicity to determine the type of x-intercept when sketching polynomials. That one there would be a saddle cut. Alright, that's all folks. Catch you in class.